This video will show you how a development tool can help you put fewer bugs into your code. Specifically, we will demonstrate how the Semel Editor uses a semantics grammar for C++ to help you generate legal C++ programs. Where do bugs come from? Edsger Dijkstra, a famous Dutch computer scientist, said, "If debugging is the process of removing software bugs, then programming must be the process of putting them in." How can we put fewer bugs in? Well, part of the answer is good habits, but a better part of the answer is to automate good habits by creating a development tool that embodies those good habits. Instead of writing a program and then giving it to a compiler, which is asking, is it legal C++? Our goal is to create a development tool that allows us to generate legal C++ programs. Our focus is not on correctness. If the definition of correctness is that it does what you want it to do, there's no way any development tool can do that. The best we can hope for is a legal program, that is, one which will compile with 0 warnings and 0 errors. We will utilize mathematical induction. The basis step is to start with something that's legal, X. The inductive step is to jump from something legal to something else legal, in other words, a legal transformation. So if you start with something legal and make one legal transformation, the result is legal. 2, 3, N legal transformations, the result is legal. So it's legal at every stage of the process. Consider a computer program that plays chess. It displays the board to you in the initial configuration, which is a legal chess game. And then it offers you a list of the only legal moves you can make. At the beginning of the game, white has exactly 20 legal moves. You choose one. The result is a legal game. The computer chooses a legal move. The result is a legal game. Here's what it looks like after white's first move and black's first move. It is a legal game. At every stage, the program offers you a choice of all of your legal moves, which is not expensive to compute and does not require artificial intelligence. You choose one, the computer considers the same, back and forth, it's always a legal game. You might win, lose, or draw, but it's guaranteed to be a legal chess game. Now let's use this analogy for C++. Instead of playing chess games, let's pretend we're playing the C++ game. And our development tool will assist you in generating legal C++ programs. We need to ask, what are the elements of a program? Are they characters, syntax tokens, or something else? Let's start with characters. Clearly, a file that is empty, containing 0 characters, will compile with no warnings and no errors. It is therefore a legal C++ program. That's the basis of the induction. At each stage, a development tool that plays the C++ game would say, here are your only legal options. Move the cursor, insert a character, remove a character. You choose one of these 3 things. Is the result a legal C++ program? Probably not. Characters are too small a level of granularity to guarantee legality. Certainly if you lather, rinse, repeat, and keep inserting characters, there's no way to guarantee that the result is, at every stage, a legal C++ program. So characters are the wrong answer. They're not the elements of a C++ program. What about syntax symbols? The definition of symbol is a sequence of one or more characters. Symbols are either terminal, which can and must be replaced, or terminal cannot be replaced. Replaced meaning replaced by, here's the rule. A grammar rule says this symbol on the left, which is a non-terminal, can be replaced by the symbol : equals dates back to BNF, Bacchus-Nauer form, and a right-hand side made up of 0 or more symbols, each of which is terminal or non-terminal. When you have a set of rules, we call it a grammar. When you have a series of symbols, we call that a sentence. And a set of sentences is a language, so a grammar can be used to generate, notice our focus is on generating, sentences in a language. So an English grammar generates sentences in English, and a C++ grammar generates sentences in C++. Here are some of the rules from the C++ 24 standard. I'm sorry for the small font. I just wanted to show you the list of ones we will be using in this example. You don't have to research this or understand this. I'll go over it step by step. But these are the ones that we will be using. Anything in double quotes is a keyword or a literal. Let's assume that your goal is to generate a definition of a local variable. So you start with a simple declaration. Digression. This is the wrong place to start. The reason is a simple declaration can occur in a namespace, but a local variable definition cannot. A simple declaration can occur in a class, but a local variable definition cannot. So we're actually starting in the wrong place, but let's put that on the shelf for now and keep going. You start with a simple declaration, which is a non-terminal. And the development tool says, here are all the ways that a simple declaration can be replaced by something else. The ... dots just mean there's alternatives. The one you want is one or more decal specifiers followed by an init declarator list followed by a literal semicolon. So you choose alternative number 2. And the simple declaration is replaced by the right-hand side, which is legal. So we start with something legal, we end up with something legal. A decal specifier plus can be replaced by one or more than one, and you choose 1. So decal specifier plus is replaced by decal specifier. You started with something legal, you end up with something legal. We're always legal at every stage of the process. Decal specifier has many different alternatives. You choose one. Defining type specifier has alternatives. You choose one. Type specifier, you choose one. Simple type specifier, you choose one. Well, now we've gone as far as we can go with the very first non-terminal. We've arrived at a literal. It's terminal. So we go to the next alternative, init declarator list. And an init declarator list can be one or more. We'll choose 1. An init declarator can become a declarator, which can become a pointer declarator, or a no pointer declarator, or an ID declarator, or an expression ID, or an unqualified ID, which becomes an identifier, which is a terminal symbol. So int is terminal, identifier is terminal, semicolon is terminal. There's no more things to replace. So we've gone as far as we can go, and we have the guarantee that this is legal syntax. Here's a summary of everything we've done with these symbols here, meaning is replaced by. So the first one is replaced by 3, and then each one is replaced going down to a terminal. Each one is replaced going down to a terminal. That's a terminal. So int identifier semicolon is at the bottom. So that's as far as we can go. The good news is we've achieved our goal. We have defined a local variable. Now there's no requirement that this has to be done left to right, top to bottom. Any non-terminal can be replaced at any time in any order. To go back one slide, after you do a few of these, you could then work on this one, and then go back over here, and then go back over here. So there's no requirement that it be depth first in any way, shape, or form. Observe that generation is the exact opposite of parsing. During parsing, you replace the right-hand side with the left. You start with the sentence at the bottom and end up with the goal at the top. Generation is the exact opposite. You start with the goal on the top and replace it with right-hand sides to end up with the sentence at the bottom. So we're doing the inverse of what a compiler front-end parser is doing. We're generating and guaranteeing a legal program at every stage. Or are we? The bad news is that a simple declaration could result in this series of reductions where the bottom terminal symbols are bool, float, mutable, const eval, explicit, ... with a terminal semicolon, and we have multiple problems with this. Number one, you can't be both bool and float. Number two, we still don't know if this is a function or a variable. And number three, simple declarations could be in namespace scope, class scope, compound statement scope. So this is really not the right answer. There are many decal specifiers. When you multiply it out, there is a huge number of permutations, sadly, most of which are illegal semantics. And we've come face to face with the fact that legal syntax does not imply or guarantee legal semantics. This does not achieve our goal. This is the wrong answer. So the elements are not syntax symbols. So if they're not characters and they're not syntax symbols, what are the elements? I'm going to come back to that in just a moment. Look at the process of programming. A programmer begins with semantics in their head. They then translate from semantics to C++ syntax, which might live in a text file, till you give it to a compiler whose job is to convert the syntax back into the semantics. Now, if we've done it right, the resulting semantics matches the semantics the programmer started with. If we've done it right. That's the whole goal of programming, is to do this translation from semantics to syntax correctly so the compiler recovers the original semantics. But this is a lossy translation. There are things the programmer can know about the semantics that are not expressible in the C++ language. So it is in principle impossible to guarantee that everything in here is preserved over here. Can we eliminate the middleman? Instead of a lossy translation into syntax and then a translation out of syntax, can we go directly from here to here? And if we could, what would that look like? And the rest of the talk will describe the answer to that question. You're familiar with the periodic table of elements. I promised you we would come back to the question of what are the elements in a C++ program. If they're not characters and they're not syntax symbols, what are they? The answer is they are semantic elements. If you take 3 letters from here and 2 letters here and make a portmanteau word, it's called a semel. That is the unit of granularity of semantics. All the semel names we will use in this discussion begin with the word semel, so it's clear that that's what we're describing. A local variable definition is a semel. A use of a local variable in expression context is a semel. A class definition is a semel. A use of a class in type context is a semel. A function is a semel. And we will end up with an inheritance relationship. There are several kinds of functions: class member functions, namespace member functions, lambdas, main functions. So there will be an inheritance hierarchy here. The definition of semantic element is a thing that has attributes and associations. An attribute is what I know about myself as a Semel. Every attribute has a name and a primitive type like bool or int or enum. And Semels have relationships to other Semels in which the Semels play roles. They have types. It could be one-to-one or one-to-many. And some relationships are ownership relationships. Other relationships are use relationships. If you're thinking this sounds like entity relationship diagrams or unified modeling language, you're exactly correct. If I use you, then I am associated to you. And that means if I am deleted, I do not cause you to be deleted. I don't own you. I merely use you. Ownership is composition. If someone deletes me and I own you, then I do delete you. Isa is inheritance. If I Isa you, then I inherit your attributes and your associations. A rule in a semantic grammar which says that a left-hand side can be replaced by a right-hand side. Rules come in two flavors: Isa rules and Hasa rules. A local variable is a statement. It's not a simple declaration. It is a Semel statement. A local variable is a variable. There are several kinds of variables: namespace member variables, class member variables, formal parameters, local variables. And a local variable has 5 attributes, 4 booleans and a string, and participates in 3 associations. These 3 happen to all be ownership. And I chose to draw this as a spreadsheet because I thought that was easier than all these Hasa rules one after the other. Now, if your goal is to generate a local variable definition, you start with a statement. And that is correct. Local variable definitions are statements, can only occur in statement context, not in a namespace, not in a class. So we're starting in the right place. Statements can be replaced by many things, including a local variable definition. So Semel statement becomes a Semel local variable. That's legal. Semel local variable is a terminal. It's not a non-terminal. It cannot be replaced, but its attributes can be changed, all of which are legal semantics. And you can add or remove to a one-to-many association or set or remove a one-to-one association. Whichever one of these 8 you choose starts with and ends with legal semantics. And you can do one or more of these changes in any order. The good news is we have succeeded in defining a local variable in statement context. You can make these 8 changes in any order at any time. Notice we started with the semantics, with the goal, with the programmer's intent. As Herb Sutter says, enable the programmer to directly express intent. Here, we're not doing it by expressing intent in syntax. We're expressing intent in semantics. And we edit the Semels in a Semel Editor. We're not editing characters. We're not editing syntax. We're editing semantic elements. So far, we haven't mentioned syntax. If you're not thinking about it, you can't make a mistake. The semantics grammar for C++24 has 454 Semels. Many are abstract, many more are concrete. So the way we've eliminated the middleman is by having a thing that edits semantic elements. So the thing that we don't know what it is an editor of Semels. It's not a text editor. It's not a syntax editor. It is a semantic element editor. And that allows you to start with and end with semantics, completely eliminating the middleman of syntax. In a sense, the Semel Editor is very similar to a compiler front end. The compiler front end reads C++ code, does lexical analysis, syntax analysis, semantics analysis, and results in intermediate language or intermediate representation. Semels are a form of intermediate language. So the Semel Editor ends up in exactly the same place as a compiler front end, but it doesn't start with a text file containing code. When we wish to translate from semantic elements to code, we codify. So inside the Semel Editor, if you wanted to codify a Semel local variable, you output the various keywords corresponding to these attributes. You codify types, the name, the attribute specifiers, the initialization, and the final literal semicolon. Which means, without any artificial intelligence at all, the Semel Editor produces the syntax for you. It doesn't make mistakes. Therefore, this whole process cannot make a syntax error. Notice that we've simply eliminated the ability to make that category of error. Our goal is to put fewer errors into the program, and this is how we achieve the goal. Here's a screenshot from the Semel Editor right after you have said, I want to make a new local variable. You have the ability to look at or modify the attributes and look at or modify the associations. An empty local variable which has an empty name says the Semel should have a name, and syntactically, over here on the right is the generated codified syntax, there's a missing name. There's also a missing type because there is no type yet. And there's the literal semicolon. So notice the syntax is telling you what to do next. The first thing you might do is set the name. So you keystroke a name in, press the Enter key, and immediately the codify on the right shows the name, and instead of saying that it should have a name, it does have a name. Now it's saying that name is not used. In the lower left-hand corner, you get feedback. These are called FYIs, for your information. These are messages that a compiler might tell you, but notice we haven't extracted the code into a text file. We haven't given it to a compiler. We haven't run a compiler over the code. And already, in the middle of editing the Semels, we're getting some of the messages that a compiler might tell you. That saves time. The earlier you find out that there's a problem, the less time it costs to fix it. The next step might be to add a type. So after you set the type to bool, it says, I know that my type is a bool. The name is still not used. What might you do next? Add an initialization to a literal of type bool, which is false. Now we have a fully initialized, defined local variable whose name is not used. Now let's use it. Let's make an expression which represents a use of a local variable. After having just created it, it says, I don't know which local variable I'm using. So the codification says you've missed out on specifying which local variable you're using. So let's click on the Change button, and up comes a pop-up that says, tell me the name, in the form of a regular expression. You can search for which name you want to use. If you type what in, it will use that. Or you could say, I feel lucky, and click on the red circle here, which says, oh, well, here are all the local variables you could use from this point in the program. There happens to be only one. It's a local variable, so you say OK, and that way the use of a local variable says, which one am I using? That one. And the local variable's name is codified here as an expression. You can navigate to the local variable that you're using, which now says, I know that I'm used by that use over there. And if you click navigate, you go back to this slide. So you can click back and forth between the you can click back and forth between the local variable and the use of the local variable. Each one knows about the other, and that's always kept synchronized. More good news, if you go to the definition of the local variable and change the spelling of the name, every use of it immediately uses the new spelling. Every Semel that is used cannot be deleted. The Semel Editor will not allow you to delete a Semel that is used. You must first remove all the uses, then you can delete the Semel. That's better than a text editor where you can delete anything, recompile, and then discover, oh wait, that was still used. The Semels store your intention. An expression that's a use of a local variable can only use a local variable, not that, not that, not that. You can only use what you said your intention is to use. And since the Semels are stored, they are persistent. Anybody looking at your Semels can see what your intention was. It's clear. It stays with the other Semels. The Semel Editor will not let you use a name that does not exist. A text editor will. The Semel Editor will not let you use a name that is out of scope. A text editor will. The Semel Editor will not let you use a name that you cannot access, like somebody else's private variable. A text editor will. The Semel Editor will not let you use the wrong kind of thing. A text editor will. The Semel Editor can see all the things that you use, and it says if you're using a Semel that is declared in a header file, you must need a hash include. So the Semel Editor synthesizes all the hash includes that you need, which means you don't have to remember which header file declares which names. And header files are always synthesized by the Semel Editor dynamically. You only use what you need, so they cannot go stale or out of date. Many times I'm sure you've seen a C++ file with a bunch of hash includes, and you don't know if some of them are no longer needed because of changes in the code. The goal of the Semel Editor is to prevent you from putting bugs into your program. You cannot have syntax errors. You cannot have stale includes. It's not a bug, but it wastes compilation time. If you don't put bugs in, you spend less time debugging, which increases your productivity. That exists today. Where will we go in the future? The Semel Editor contains all the Semels in your program which you've input and all the Semels from the standard library, which I've input. Given total knowledge of your entire program, what can we do with that? The Semel Editor could generate runtime reflection. I don't mean the new compile time reflection that's going to be in C++ 26. I mean, given a pointer to an object at runtime or a reference, you can say, which class am I an instance of? What are that class's members? This is similar to Java reflection. You can say, find all Semels that match a pattern. A pattern might be an assignment from an expression of type int into a variable of type float. Identify all constraints on a template based on usage. Instead of doing that by hand, the Semel Editor could do it for you. Given a set of constraints, which templates satisfy those constraints? Tell me which exceptions could be thrown during the invocation of this expression or statement or function. And again, because we have the whole function call graph, we can determine that during Semel Editor time. We can do interprocedural data flow analysis, interprocedural control flow analysis, optimizations, type inference of variables from usage. We could add a class browser. Since the Semel Editor is like the front end of a compiler, we could add a back end and generate code. We could add a debugger. We could have incremental compilation. We could add an interpreter. We could add a pretty printer. You could say, I want my braces at the end of the previous line instead of the beginning of the next line. And all codification would observe your indenting style. We could add design patterns and refactorings. So there are many optional future directions. We could add support for things you wish you could express in the C++ language, but currently cannot. In Java, you can say a class is an interface. Wouldn't it be nice to be able to say that in the Semel Editor, even if you cannot say that in C++? Are you clonable? Are you abstract? Are you concrete? Are you reference semantics, value semantics? Are you immutable? Are you or are you not default constructible? We could add access control lists. Instead of saying that a data member is private, we could say it's only usable by these functions, whether they're in or out of the class. That's a finer grain granularity of access control than public, protected, private, and friend would give you. When you add a data member, if you say, how is it initialized, copied, assigned, tested, cleaned up, and converted to a string, you could synthesize a constructor by saying, add up all the initializations for all the data members, and that's a constructor. Add up all the copies for all the data members, and that's a copy constructor. Add up all the assignments for all the data members, and that's an assignment operator. Now, clearly, such functions might do more than this, but if that's all they need to do, these could be synthesized from that. We could enforce style guidelines. All abstract classes might conform to this pattern. All constructors might conform to this pattern. You could say, although it's legal to have goto in C++, I don't want to allow goto statements. You could say, although it's legal to have an increment operator embedded in a larger expression, I don't want to allow that. You could prevent non-virtual functions from being overridden. There's no way to do that in C++. It used to be that there was no way to prevent a virtual function from being overridden, but now you can say that in C++. Future directions might include adding enough Semels to support other languages. Right now, we support C++, 98, 03, 11, 14, 17, 20, and 24, but we might also allow you to turn the knob and support C++ or Java. Eventually, there'll be enough Semels to support all of these languages. I hope that I've succeeded in showing you how a semantics grammar-based Semel editor can help you put fewer bugs into your code. Thank you so much for watching this. If you have any questions, please feel free to email me. I'll be more than happy to answer your questions.